All right, welcome to our first recorded lecture here for the start of Chapter 4 material. A lot of what we're about to see is still really going to be similar to kind of some of the things we were doing at the end of Chapter 3 with stoichiometry. We'll see probably in class some examples even with things like limiting reagents applied to solutions also. But really kind of this first part of Chapter 4 just kind of deals with what happens when we don't just have like plain solids, right? Everything we've been looking at so far is involving like masses of these compounds that are reacting, but the reality is we rarely ever take two solids and like throw into a container and like shake them up and have an effective reaction take place. Um, from a kind of just practical aspect, most of our reactions are going to take place in what we call solutions. So as a starting point, I'm going to talk a little bit about some terminology dealing with solutions so people kind of understand what things are being talked about or referenced as we hear kind of some different pieces talked about. First off, when we just start with the term solution itself, it's basically a homogeneous mixture. And if we think back to kind of early on in chapter 1, we had some other definitions as well, and homogeneous mixtures were one of them. And I'll back up 1 second. And the homogeneous mixture basically just means we have kind of an even mixture of everything throughout. So it's a consistent composition anywhere in that particular system that you're looking at. Now, solutions have kind of a couple components. The major one we refer to as the solvent, and most of the time when we're talking about solutions from kind of a lab perspective for general chemistry, the solvent is usually the liquid that something's dissolved in. More often than not, you have solids dissolved in liquids is how most of your solutions are formed, although there are other kind of physical state possibilities there. So don't always assume you have to have like a solid dissolved in a liquid to make a solution. There are other actual ways to make solutions. It just so happens that's the easiest way to do it for most chemical reactions that you would do in a normal laboratory setting, especially for general chemistry type course. Now, the other component of your solution besides the solvent is what we call the solute. And so again, if you have kind of like solids being dissolved in liquids, like your liquid's kind of the major component, it's the solvent. And if you have whatever your solid is that you're trying to dissolve in it, that's what we refer to as our solute. And this is usually this compound or the substance that we're interested in. And when we talk about what we call concentrations, the concentrations are usually going to deal with the amount of the solute that are in your particular solution. Now, when I just mentioned the term concentration, and the major way we actually kind of express concentration, which is really a representation of how much solute is in the solvent, is going to be through using what we call molarity. There are other units of concentration that we will talk a lot about in 1212, but for 1211, we mainly tend to focus just on molarity for right now. And the way we calculate molarity for any solution is we take the moles of our solute and we divide it by the entire volume in liters of our solution. And so molarity, we will see its unit as capital M, but its units do break down into moles over liters. Now, in terms of making solutions, because this is something that if you haven't done in lab already, you probably will this coming week or in the coming weeks. And there's a couple different ways to go about it. I'm going to outline kind of two very common ways of doing it right now. If you have a solid solute, a lot of times the most common way you're going to go about making that solution is you're going to kind of pick a target volume that you would like to make. Ideally, it's probably going to be like 100 or maybe 250 or 1,000 milliliters, which would be 1 liter. And the reason I say those is because a lot of the times if you have a solid, what you're going to do is dissolve that compound in your solvent inside something called a volumetric flask. And the sizes, the volumes I gave, those are common sizes for volumetric flasks. And the way these volumetric flasks work is they have a little marking. You can't really see it in this image, but they have a little marking here somewhere along their neck. And if you fill the volume level up to that marking on the neck, it is exactly whatever its volume is. So if you have a 100 milliliter volumetric flask, filling it to that exact line on its neck is not just like 100, but like 100.00. I have a few decimal places worth of kind of accuracy to that measurement. It's more accurate than kind of typical graduated cylinders are. And that's why they call these things volumetric flasks. Glass ones are fairly expensive, which is why probably in the Gen Chem lab you'll actually see plastic versions of really the kind of the same thing. They'll have markings for those same kinds of measurements. And typically the best way to use them is you can take your solid, add it to the volumetric flask, and you're going to add water, but not all the way up to the exact marking on the neck yet. You might fill it up to the start of the neck, and then you're going to shake up and mix up your solution really, really good so that all of your solid solute dissolves or dissociates into your solution. And then what you can do is you can take a pipette or something that has a very controlled amount of water that you can add to just barely get to exactly where that line is on the neck of your flask so that you have the exact volume that the flask represents. And now you have, if you know then that total volume, if you have a particular concentration you would like, then you can kind of figure out, well, how many moles of my compound do I need? And you can convert that then to a mass that you can mass out ahead of time to basically get the process started. So you will see some various calculations as far as making solutions, both in lab and in lecture, that may involve things like, here is the amount of material that I'm going to start with, here's the volume of the solution I'm going to make, what's the concentration. But from a lab kind of practicality standpoint of what you'd really be doing most often, you'll probably have a volume of solution that you want of a specific concentration, which means you can figure out the moles of your solute that you want, which you can, again, you convert to a mass, and you can kind of mass that out. And that's kind of the progression of things. You can figure out how much of this solid you really need to make your solution before you actually make it. You mass that amount out, put it in the volumetric, dissolve it all up, and then take it to that final volume that you were looking for, so that you have the proper concentration. So that's kind of probably the most common way of going about making solutions. Particularly, like I said, if you're in a lab setting, like, and you're making the solution yourself, like, this is probably going to be the way that you're making that solution. There is another way that we'll talk about in a little bit involving dilutions, but before we get there, again, I want to kind of show the calculations that I just kind of verbally described. So an example of this would be, what is the molarity of KBr if 25.5 grams of that potassium bromide are dissolved in enough water to make a 1.75 liter solution? So again, in general, molarity is just the moles of our solute divided by the total volume of our entire solution. And we have the volume of the solution actually already given to us. So the only thing we really need is moles of KBr. Right? We don't have moles specifically, but we do have grams. So at this point, we should be pretty comfortable converting grams into moles. So we can take the grams of KBr divided by its molar mass of about 119 grams per mole, and we can figure out how many moles of potassium bromide are in this solution. Then we can simply take the moles of the KBr divided by our total volume, and we get a molarity. And we see in this case it's about 0.122 molar. Now, I do want to kind of highlight, what types of numerical values you will typically see for molarity. First off, it does always have to be a positive value. No, you'll never have a negative molarity. But additionally, you won't see really big numbers for molarity. The highest ones I can kind of think of might be, I want to say glacial acetic acid's like 55 molar roughly, or 56 molar maybe even. That's about the highest concentration I can think of anything off the top of my head. Usually if you have a concentration that's above 1 molar, that's a really concentrated solution. You are much, much, much more likely to see concentrations that are smaller than 1 most of the time, like what this one is, like 0.122, or even like things like times 10 to the minus 3 or 4th molar are very common. You'll hear people talk about like millimolar or micromolar for very small concentrations, because those are reasonably common for different particular reaction types or applications that you're trying to use things for. Whereas the flip side of that, really high concentrations, they're just not that common, and they're also not that commonly used for a lot of different things. And so it's kind of something to be aware of. Like if you're doing calculations where you're calculating the molarity of something, like you shouldn't expect to get a number that's like 10,000 or like a million. Like if you get those for answers of molarity, you have definitely messed up some units somewhere that you need to go back and check. And that's kind of the notes that I've kind of added here in terms of molarity. Some general things, like anytime you're finding it, just kind of keep these in mind. And as we talk about dilutions here in a moment too, then we'll have a little bit more to add to this. So another kind of type of calculation, again, we'll take a look at. How many liters of 1.25 molar sodium hydroxide contains 4.55 grams of sodium hydroxide? And so this is kind of to show just another application of things, and the fact that molarity, much like density kind of previously, can also be used as really a conversion factor for dimensional analysis. So a problem like this, we have two numbers that are in our starting problem. We have 4.55 grams of sodium hydroxide and 1.25 molar of that sodium hydroxide. Well, the key is this capital M being molarity is really moles over liter, so it's kind of a conversion factor between two different units. And so we can actually set this problem up with really dimensional analysis and kind of take that into account in terms of knowing, like, are we multiplying, are we dividing, like how do we have to do this? You don't have to think of equations, just think about the units of things. Now, that said, we do have our second number is grams, not moles, which this was moles over liters. So that means we are going to want our grams in units of moles instead. So pretty similar, excuse me again, oh man. We do want our moles instead of the grams as kind of a common first step, like all the ones we were doing in chapter 3. Right, so previously we've been doing a lot of mole and gram conversions, so nothing really different here. We can convert our grams to our moles. So we can start with that, 4.55 grams sodium hydroxide, divide by molar mass, about 0.114 moles of sodium hydroxide. And then the next step you're noticing, and here on the slide, I'm showing it as divided by 1.25 molar. But really, this is the same thing as if I were to multiply by 1 mole of the sodium hydroxide divided by the 1.25 moles. I'm sorry, 1 liter of the sodium hydroxide solution over 1.25 molar. So the units on molarity, again, remember that they are moles over liters. So that when we have just the moles, if we divide by the moles over liters, that's why we got the liters here, which is kind of the dimensional analysis part I was trying to kind of describe just a second ago, where you can really write this as, 1 liter of the sodium hydroxide solution divided by 1.25 moles of sodium hydroxide. That's kind of the conversion factor you can imagine this as, which will end up with our final units of liters that we want, which are about 0.0912 liters. Which means we have about 91.2 milliliters of our solution will contain 4.55 grams of that sodium hydroxide. All right. Now, the other way we can go about making solutions, other than just like taking a solid and dissolving a solid into a specific amount of solvent, the other way we can do or make solutions with particular concentrations is through something called a dilution. So what a dilution is, and you've probably heard the term like dilute or diluted, things like that before, usually means things are fairly low concentration. And that's basically what you're doing with a dilution is you're making something a lower concentration than what we started. And so an example of this is you have some sort of solution that you begin with. You're basically just going to add more solvent, which results in an increase in the total volume, though the moles of the compound stay the same. And then the result is your concentration goes down because of that volume increase. Now, the part that I mentioned as far as the moles not changing is actually really important because it actually allows us to kind of use this little simple equation, knowing that the moles of our solution for any solution are always going to be the molarity times the volume in units of liters. And this is where you will sometimes see this equation that kind of pertains specifically to dilutions, this M1V1 equals M2V2, where capital M that here is the molarity. So the molarity that you start with times your starting volume has to equal your final molarity times the final volume. And these products should be the same because really your moles aren't changing, and that's what each of these products equal is going to be moles. And so taking that into account, whatever your starting concentration and volume are, your volume is going to increase because you're adding more solvent anytime you do a dilution. So V2 is going to get bigger, but as V2 gets bigger, M2 should always get smaller to kind of balance that and keep those products equal to each other. And so if your volume doubles, the molarity will halve, for instance. So they are kind of related in that manner. Now, doing dilutions to try and make specific concentrations, you can do this a lot of different ways. But again, making an actual solution, if you were doing this in the lab, what you can do is, again, using a volumetric flask, you can kind of do the calculation in advance. Like if you know what your starting concentration is and you know what your final concentration and volume need to be, you can actually figure out what volume of your starting solution you should begin with, and then you just add solvent to get to that final total volume that you want. And so one thing I will kind of note of this, if you have, say, like 10 milliliters of solution and you need your final solution to be 100 milliliters, like you're going to be adding 90 milliliters basically of the solvent in that case to get to that new total volume. So you do kind of have to kind of keep track of starting and ending volumes versus what you have to add because they're not necessarily really the same thing. All right, so let's see just a very quick example of this. Again, we'll have kind of more of them in the actual lecture itself that we can talk about. So here we're asked, to what volume must a 3.00 liter solution with a concentration of 0.500 molar be diluted to have a final concentration of 0.175 molar? So set up for this. As soon as you see the word dilution or diluted as part of a problem, you can pretty much just instantly kind of go to this M1V1 equals M2V2 equation to deal with that kind of calculation and set things up. So if I'm looking here, I have a 3-liter solution, concentration of 0.5 molar. That means I have M1 and V1 that have been given. And I want a final concentration of 0.175 molar. So actually no M2, I'm just looking for V2. And again, since my concentration went from 0.5 to 0.175, the concentration should always be going down during dilution, which means the volume must be going up. So what I can do to kind of set all of this up, I can go ahead and put in here's my V1 and my M1, this is my M2, and really I just have an equation that I'm solving for V2 at this point. So I can take M1 times V1, 0.500 molar times 3 liters, divided by 0.175 molar, that final concentration we want. We get about 8.57 liters. Now, this is the total volume that we have to end at, but do keep in mind, if we started with 3 liters already, we're actually only adding the difference between these two, which would be about 5.57 liters. So do kind of have that in mind if you're like, again, in a lab setting, actually having to do these dilutions in terms of exactly what you're going to be doing, and in what these numbers that we're getting out of this M1V1 equals M2V2, equation actually tell us. Now, the next kind of expansion of all of this is really just basically looking at stoichiometry problems, but dealing with solutions instead of just masses like we were doing before. And the reality is, the general steps are still pretty much the same. How we do maybe the first and possibly the last step also might be a little bit different. So in general, our starting point, instead of starting with like a plain mass and using a molar mass to get to moles, we'll probably be starting with a plain volume. And if you take a volume times the molarity of something, that will give you moles instead. And then we'll have a middle mole to mole ratio for moles of one compound to moles of another. This looks just like all the other stoichiometry problems we've been doing. We just will want a balanced chemical equation to be able to help us with that. And then our last step, depending on kind of what it is we're actually looking for, if we're looking for a volume, we can take the moles and really, in this case, divide by molarity to get a volume. It would be kind of that backwards change compared to what we started with. So let's take a look at an example for this. So here it asks us what volume in liters of 0.150 molar KCl solution is required to completely react with 0.150 liters of 0.175 molar lead 2 nitrate specifically. And it occurs according to the reaction that's given to us. We have 2 KCl plus PbNO3 is making PbCl2 as our solid. That's what we're actually going to call our precipitate or tap coming out of this reaction. And then we also get 2 potassium nitrate, the KNO3, as a product here. So how can we do this? I'm going to show this, again, slides I like to do kind of step by step. Once we're in the lecture, I'll demonstrate a lot of kind of the dimensional analysis setup for some of these types of problems, as I do think that is, in my opinion, the better way of doing a lot of this. I think it makes more sense, but I like to have examples of each for people that are interested, because I don't always have time in class to show all the different possible ways of doing something. We just don't have that much time, unfortunately. So starting point, we can find our moles of lead nitrate, since if we're looking up here, if you're trying to figure out why do I start with lead nitrate, well, I'm asked about how much KCl I'm going to need in liters. But I have, for the lead, I have both a concentration and a volume. And that's how you really pick out starting points for solution stoichiometry. Look for the compound that you have a volume and a concentration for, or that you have the information to get both of those pieces for. So in this case, I can convert my lead nitrate from the concentration 0.175 molar and the volume of 0.150 liters by multiplying these two together. Again, molarity is moles over liters. The liters can cancel. And I get the moles of lead nitrate that should be here in this reaction. And then I can convert my moles of KCl with stoichiometry. And so, again, paying attention to kind of the balanced equation at this point, for every 1 mole of lead nitrate that I have that reacts, I actually need 2 moles of potassium chloride in order to completely react away the lead nitrate. So I can take my moles of, slutty ons. I can take my moles of lead nitrate and go ahead and use that with the mole-to-mole ratio here. I'm dividing by my moles of lead nitrate now, where I only need 1 mole of lead nitrate, but I need 2 moles of KCl to do the reaction. And again, top and bottom is just so that I'm canceling moles of lead nitrate. KCl is the compound I'm interested in, and the numbers that are going here are just the coefficients, right? We have 2 for KCl and 1 for the lead nitrate. So this lets me figure out then the moles of KCl. And the last part of this is if I want a volume, notice I have a concentration. Right, so if I want to find the volume, I can take the moles and I can divide that by the concentration. So in this case, I'll be dividing by 0.150, and that should give me the proper units so that I end in liters, which when I do here looks like it comes out to about 0.350 liters. And if I stop to think about things for a second, that should hopefully make sense overall. I have similar concentrations for KCl and PbNO3, but I need twice as much KCl. So as a result, I do expect the concentration of KCl to be considerably higher in order for us to have enough of it to react. And in fact, it should be almost twice as much because of that 2-to-1 ratio here if the concentrations are similar. So like if we double 0.175, that's 0.350 if we're doubling it. And then that should hopefully make sense. I'm sorry, we'll take 0.150 and double it, it's 0.3. We're actually a little bit over that because the concentration for KCl is a little bit less. And so we're probably going to have to more than double it to have enough KCl for the reaction. That's kind of what we see for the numbers here at the end. So do try to take some time at the end of problems to reason through, like, do the answers make sense for any volumes or concentrations and whatnot that we're calculating. That does go a long way to kind of checking your work to make sure things have kind of gone properly. So here's another one. Here we're asked what mass of CO2 will be produced if 55.0 milliliters of 0.150 molar nitric acid are reacted with 35.0 milliliters of 0.108 molar sodium carbonate by the following reaction. Now, in terms of solving this, even though this is dealing with solutions, the situation is the same as limiting reagent and theoretical yield problems we saw previously. Right? We effectively, instead of having just a mass of all of our starting samples, we have volumes and concentrations. Well, what do volumes and concentrations let us find but moles? So really, we can do this the same way we did all of our previous examples for stoichiometry before. The only difference is instead of having mass and dividing by a molar mass, is instead we can start with a volume and we can multiply by a molarity to get moles for our compounds. But our goal is really to figure out how much CO2 can we make from each of these amounts of starting materials. So, oops, for some reason my calculation here is unfortunately no longer sizes properly into the slide. So let me apologize for that as I fix it really quickly here, hopefully. Let's see if it'll respond and let me get our slide. There we go. Sorry about that. It hopefully looks much better. And this should look hopefully again familiar in terms of setup. Here we have a volume times a concentration. This is going to give us the moles of HNO3. And then I can use a mole to mole ratio. This is the stoichiometric ratio, right, that we're used to using to go from our balanced reaction. It takes 2 moles of HNO3 to make 1 mole of CO2 in this balanced reaction. So that's why I see the 2 on bottom, 1 on the top. This will tell me the moles of CO2 I want. At the end, I want a mass. I don't have to get the mass this second, although if I was doing this all in dimensional analysis, I probably would just take it all the way to the mass because that would make it a little bit easier, which I think would be multiplying this final number of moles of CO2 by 44.01 is going to be that molar mass we see in a second. Now, I can take the same approach for the sodium carbonate. Right? I can take the volume of the sodium carbonate times its concentration. That'll give me the moles of sodium carbonate. That's a 1-to-1 ratio of things. Which is then going to produce about 3.78 times 10 to the minus 3 moles of CO2, which is actually slightly less than what we should have gotten from the nitric acid. What that means is that since the nitric acid produced, I'm sorry, not the nitric acid, since the sodium carbonate, the Na2CO3, produced less CO2, this should be our maximum theoretical yield, and the sodium carbonate itself is going to be the limiting reagent in this case. So sodium carbonate is limiting. I can calculate the theoretical yield in grams if I want to now for the carbon dioxide by taking this number of moles, right, my theoretical yield, and go ahead and multiplying by the molar mass of CO2, that 44.01, and I get about 0.166 grams of CO2. I think had you gone straight to grams in the top one, I believe it's like 0.181 grams, if I remember right, or something in that general vicinity, which is, again, bigger. So the limiting reagent is the sodium carbonate. Here, this number of moles, or 0.166 grams, are going to be our theoretical yield, which is then the maximum mass of CO2 that we would expect to be able to produce.